Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. So today we're going to step in the second chapter entitled Fourier series. So these are the main topics that will be covered in this chapter, including the signal expression in time domain, in frequency domain, or known as spectrum, and also in complex exponential. So what is Fourier series? Fourier series is developed to represent infinite sum of periodic signals, either it is in sines, cosines, or exponential form. So these are the examples of periodic signals in different shapes. So let's recall from the first chapter, periodic signals is basically a signal that repeats itself by fundamental period T0. Okay, so n is the number of harmonics, the number of next sequence from the first fundamental period. So for example, in the first signal, so this is the T0. Okay, so the signal repeats itself by the same T0. So Fourier series commonly used in various applications such as listed, and Fourier series can be represented in two forms, either in trigonometric or complex exponential form. Okay, sinusoidal signal is a common types of signal used in communication systems, either it is in sines or in cosine function. Okay, this is the general equation if we have a cosine signal, so in which A0 is the peak amplitude of the signal and omega naught is the angular frequency in radian per second, and theta is the phase of the signal. So this equation can also be written in sine function, in which A sine omega naught t, if you convert to cos, there's a negative pi over 2 phase shift of the signal. So omega naught is the angular frequency in radian per second, and it is equal to 2 pi f naught. F is in hertz, frequency in hertz. It's equal to 1 over t, in which it is a fundamental period in second. Okay, let's look at how the sine and cosine signal looks like in time domain. So the brown graph is for cosine signal, and the blue one is the sine signal. So if you look at the equation, the sine signal is basically a cos signal that being shifted to the right by pi over 2 or by 90 degree. So if you look at the equation, equal to cos omega naught t minus positive pi over 2. So the signal being shifted to the right by pi over 2. So if you look at this graph, the cosine signal, okay, so the sine signal, this one is basically the cosine signal that being shifted to the right by 90 degree. Okay, the signal, sine or cosine signal, can also be represented in frequency domain, or also called a spectrum. Okay, spectrum meaning the signal being plotted in frequency domain, the signal in time domain being plotted in frequency domain. So frequency domain can be either in hertz, f, or in omega, radian per second. So you need to be consistent. If you use f in equation, so make sure you use f in the graph as well. So for example, if you have this equation for Vt, so how to plot a single-sided spectrum? Okay, so this equation is also known as trigonometric function, or also known as polar form. When you have sine or cosine function, in an equation, so it is also called trigonometric or polar form. Okay, so to plot a single-sided spectrum, you need to separate the amplitude spectrum and also the phase spectrum. Okay, so first one, so you need to identify the frequency, how many frequency components you have in the equation. So for this particular example, you have two frequencies. The first one is this one, omega 1, and the second one you have omega 2. Okay, so for amplitude spectrum at omega 1, the amplitude is A1. So this is A1. So at omega 2, the amplitude is A2. Same goes to the phase spectrum. When you have omega 1, the phase is theta 1. So when the frequency is omega 2, so the phase is negative theta 2. So that's why the signal pointing down. Okay, let's look at this example. So plot the amplitude and phase spectrum for the given signal. So the first step is you need to rewrite the equation. So there's a hint on the right hand side. When you have negative cos, you can convert it into positive cos by having the positive pi phase shift. If you have sine equation, so you can convert this equation, this sine function into cos by having a negative pi over 2 phase shift. Okay, so rewrite the equation. Okay, so this remain the same, a cos omega naught t, and here you can notice it is negative b cos 2 omega naught t. So this is the second frequency, and negative can be converted into positive by having positive pi phase shift. And the third one, you have a sine function, you can convert it into cos by having negative pi over 2 phase shift. So let's draw the amplitude spectrum. So the first one, you have omega naught. So this is omega naught. The amplitude is A. And then the second one is 2 omega naught. The amplitude is B. And the third one is 3 omega naught, and the amplitude is C. And don't forget, a spectrum, you have the x-axis will be in frequency, either in hertz f or omega in radian per second. Next one, you need to plot the phase spectrum. So for the first one, you have omega naught. So omega naught, there's no phase shift, so it is 0 at omega naught. And then at 2 omega naught, you have positive pi, and then at 3 omega naught, you have negative pi over 2. So remember, if you need to plot a spectrum, make sure you plot both the amplitude and the phase spectrum. Okay, let's look at another condition. When you have both cos function and sine function that share the same frequency, omega naught or omega n. Okay, so in this case, you need to rewrite the equation into an equivalent equation given by an cos omega n t plus theta n. So to calculate the an, it is equal to an squared plus bn squared, and theta n given by inverse tangent of negative bn over an. So this is basically the coefficient of the function. Okay, so please notice that an is basically for the cosine equation, while bn is for sine equation. Okay, let's look at an example. So you need to plot a magnitude and phase spectrum of the given signal. So the first step, you need to check the component given and rewrite if necessary. Okay, so in this case, let's look at the given function. So the first one you have here is when omega naught equal to 0. So this is, you have the first frequency omega naught in sine function, and you have also omega naught frequency for cos function. So obviously you'll notice that this sine and cos function sharing the same frequency. So you need to rewrite this equation by using the equivalent function. So the third component here, you have negative cos. So you can convert this negative into positive by having the by having the phase shift of positive pi. Okay, so this is the equivalent function. So you need to determine what is the an, omega n, and also theta n. Okay, so this general equation, the equivalent equation, is equal to an. An is the coefficients for the cos function and bn for the sine function. So let's compare the general equation with the equation you have. Okay, so in this case, cos function you have an. So in this case, an equal to 2. So for sine function you have bn. So bn in this case is 1. Okay, so to calculate the amplitude an, it is an squared plus bn squared square root. So this is for your an is 2 squared plus bn 1 squared. So you get an equal to 5 square root of 5. While theta n equal to inverse tangent of negative bn divided by an. So inverse tangent of bn in this case is 1. So an is 2. So you get theta n equal to negative 26.56 degree. Okay, from the previous slides, we have calculated the an, in which an equal to square root of 5, while theta n equal to negative 26.56 degree. Okay, so then you need to rewrite the complete equation. Okay, Vt is equal to 1, and this is the equivalent equation, plus the third component. So it's negative. Now you have changed it into positive by having positive pi phase shift. So now replace an by square root of 5 and then theta n by 26.56. Okay, so let's draw or sketch the spectrum. So in this case, you have at 0 you have amplitude 1, at omega naught you have amplitude square root of 5, at 2 omega naught the amplitude is 2. Okay, next is the phase spectrum. At 0 there's no phase shift, so 0 is 0. At omega naught the phase shift is negative 26.56, and then 2 omega naught you have 5 pi over 4, which is equivalent to 225 degree. Okay, this is the first representation of the trigonometric equation, in which we have the imaginary and real part, and the direction of the angle is basically anti-clockwise for positive phase value, while if you have negative phase, the lines will be pointing downwards. Okay, the trigonometric equation, so again this is trigonometric equation, can also be represented in complex exponential form by using Euler's theorem. Okay, we can get the equivalent exponential form for cosine and sine function. So for sine function, omega t plus theta is equivalent to ej whatever in the bracket. So this is the bracket, so e positive j whatever inside the bracket minus e minus j whatever inside the bracket divided by 2j. So this is derived from the Euler's theorem. So this is the Euler's theorem, and for cosine function is equivalent to e positive j whatever inside the bracket plus e negative j whatever inside the bracket divided by 2. So if you look at the difference between sine and cosine, you have negative for sine but positive for cosine. For sine function, it's divided by 2j, while cosine function divided by 2. So in summary, so when you have this trigonometric function, it can be written in exponential form by using the Euler's theorem. And this trigonometric function can also be called polar form or time signal expression in time domain. Okay, while the exponential form is called complex exponential function. Okay, if you have an equation in exponential form, so you may plot a double-sided spectrum, both for the amplitude and also the phase. Okay, if you still remember, in a trigonometric form, you only have single-sided. What does it mean by single-sided? Meaning that you have all signals on the right-hand side, omega naught, 2 omega naught, and so on. This for the amplitude. Same goes to the phase. So this is single-sided. And it is for the trigonometric equation. But for the exponential form, you will be having double-sided. Double-sided meaning that you have both the negative frequency and positive frequency in your sketch. Same goes to the phase spectrum. Okay, if you look at this equation, so you have the amplitude of V0 over 2. For this is the positive frequency. Okay, positive frequency. So the amplitude is V0 over 2. And for negative, okay, if you expand the equation, this is negative omega. So for negative frequency, the amplitude also V0 over 2. Okay, let's look at the phase spectrum. At positive frequency, okay, at positive frequency, okay, the phase is positive theta. At positive frequency, it's positive theta. But at negative frequency, negative omega, so the theta is negative multiplied with positive, you got negative theta. Okay, so this is the double-sided spectrum for exponential form. Okay, same goes to phasor representation. If you have a trigonometric form, so the phasor diagram will be in only single-sided, only one side. But for exponential form, you have double-sided, one on top and one at the bottom. Okay, if you look at the frequency, so at positive frequency, you have positive theta. So that's why it's pointing to anti-clockwise. But for negative frequency, okay, so it's pointing downward. Okay, because you have negative phase shift. Okay, in summary, when you have both trigonometric or polar form, so this is trigonometric or polar form, and this is the exponential form. So you'll be having a single-sided spectrum for both amplitude and phase for trigonometric function. But for exponential Fourier series, you'll be having double-sided amplitude and phase spectrum. Okay, let's look at this example. So given xt, a continuous time periodic signal, so you need to represent the signal in complex exponential Fourier series. Okay, so in order to do that, you need to convert each of these into exponential form by using the Euler's theorem and then sketch double-sided. once you have exponential Fourier series, obviously you'll be having double-sided spectrum. Okay, let's look at the component. Is there any frequency sharing? Look at the omega. So this is 0. So this is the first omega, and this is the second omega. Obviously, there's no frequency sharing. Okay, so now rewrite the equation into equivalent equation or in exponential form. So I will advise you to convert the sine function into cosine function. So it will be much easier to process later on. Or else you can also convert the sine function straight away into exponential form by using the Euler's theorem, in which for sine function, for example, sine theta is equal to e j theta minus e minus j theta divided by 2j. So it'll be a bit confusing sometimes when you have j at the bottom and you need to play around with the phase shift. That's why I would recommend you to convert all sine function into cosine function first. Okay, so when you rewrite, so this is the first component, this is a cosine function, and then plus convert the sine function into cosine function, you'll be having a phase shift of negative pi over 2. Okay, so now convert each of the component into exponential form. Okay, so this is the constant. So for cosine function is e j positive j whatever inside the bracket plus e minus j whatever inside the bracket divided by 2. Okay, so plus 4 e j whatever inside the bracket, just copy whatever inside the bracket, plus e minus j whatever inside the bracket divided by 2. Okay, so now simplify the equation. So you get xt equal to the following equation. So now let's plot the spectrum. Okay, let's start with the first spectrum, amplitude spectrum. So you have 0, 0 here, so the magnitude is 2. And then you have the first frequency 2 pi over 3. Okay, and you have negative 2 pi over 3. The magnitude both is 0.5. This is 0.5. And then at 5 pi over 3, the third frequency, and negative 5 pi over 3, the amplitude is 2. So this is 2. Okay, don't forget to put the axis, and the unit is radian per second. Okay, next is the phase spectrum. Look at the first one. This is 0 when omega equal to 0. So there's no phase shift, so it's 0 here. And then when omega equal to positive 2 pi over 3, positive 2 pi over 3, and negative 2 pi over 3, there's no phase shift, also 0. And the third frequency at 5 pi over 3, so positive multiply with negative, you get negative pi over 2 at positive frequency, and at negative frequency, negative 5 pi over 3, you get negative times negative positive, so you get positive pi over 2. Okay, so this is both the amplitude and phase spectrum of the given function. Okay, these are some of the equivalent function that may be useful in your equation, in your derivation. So that's all for this session. Thank you.